eigenvalues. So for this one, 0, negative 1, 1, 0, we found this on the very, very first problem on this packet. We found that the two eigenvalues were I and negative I. I'm going to set lambda 1 to be I and lambda 2 to be negative I, and we're going to see what happens. So we need to find the matrix A minus lambda I. So I'm going to have negative I, negative 1, 0, 1, negative I, 0. Oh. So with this is not something that we really want to have to reduce. This looks kind of messy, and it's not going to be necessary. So we know that this is going to give us our eigenvectors. We know that we're going to have infinite solutions because we haven't made any mistakes. So what we're going to do, or what I'm going to do, is I'm going to look at these two equations, or I'm going to look at these two rows in their equation form. So if I take a look at this top line, that's going to give me the equation negative ix1 minus x2 equals 0. The bottom is going to give me x1 minus ix2 equals 0. So both of these equations, they're going to give us the same vector. They're essentially going to give us the same solution no matter what. So if they're both going to give us the same solution, pick one to work with. And I usually work with the second one just because I like having that coefficient for x1 being 1 already. So if we look at just this second equation, so I have x1 minus ix2. So x1 equals ix2. So if we look at this in vector form, so we can say x2 is free. And let's see if we remember how to do this. So if x1 is ix2 and x2 is free, so that would mean that x2 is x2. This is going to give us the vector I1. And hopefully we remember how to go from this form to vector form. I know that I'm making this video before we have our Zoom class, but I know we're going to do it as part of the Zoom class a little bit, so hopefully we remember. But to go back and explain a little bit, so we found this. We found the matrix associated with the first eigenvalue. Instead of reducing the matrix, I switched it into its equation form. Both equations would give us the same vector. Both of these equations would give us the same vector. Maybe in a different form, but it would be essentially the same thing, maybe just a multiple of it. But both equations give the same solution, so you can choose one that's easier to work with. Typically, the bottom equation will be easier to work with because the coefficient for x1 is a little bit easier to work with when it's real, as opposed to the first equation, the coefficient for x1 is going to be imaginary. So it's just typically easier to work with the second one, although you could use either equation. You figure out the solution that goes with that equation that you choose, and you translate it into vector form. So looking at that, we are going to try the second eigenvalue. Lambda 2 is negative I. And I want you to pause this video, see if you can do that on your own, and then come back to the video and we'll see how you do. With lambda 2 is negative I, we're going to have the matrix I, negative 1, 1, I. Oh, I forgot my zeros. And again, I'm not going to reduce it. I'm going to just take the equations associated with the two rows and thinking ahead, knowing that I like to work with the second equation better, just personal preference, I'm going to go ahead and grab that second equation. So I would have x1 plus ix2 equals 0. So x1 is negative ix2, which looks a lot like the first problem, or the first part of this problem, just with a negative I instead of a positive I. So if I let x2 be free, my vector is going to be negative I and 1. So hopefully that worked out for us. You are now going to try number 8 on your own. If you want to just do the first one, or sorry, did I say 8? I meant number 9, the next problem. So 3 over, whoops, sorry about that. By this next problem, we found the eigenvectors earlier, the eigenvalues earlier in this video. We found them to be 0.8 plus or minus 0.6 I. So I am going to do lambda 1 is 0.8 plus 0.6 I. So I'm going to do this. That's what I'm going to do first, and then I'll do the second one. So if you want to try it on your own, then pause this video, give it a shot, and then come back to the video. For this first one, so if I do 0.5 minus 0.8 plus 6i, I'm going to have negative 0.3 minus 0.6i, and then I'm going to have negative 0.6, 0. Here I'm going to have 0.75 still, and then this next one, 0.3 minus 0.6i, and then 0. Again, I'm just going to look at the second line because that's just what I do. That's what I prefer. So if I have 0.75 x1 plus, and then this whole thing would be my coefficient for x2. And if my goal is to get x1 by itself, I'm going to have 0.75 x1 equals negative 0.3 minus 0.6i x2. So x1 is going to be negative 0.3 plus 0.6i all over 0.75 is kind of ugly. But we can simplify. 0.3 over 0.75 is going to be negative 0.4. 0.6 over 0.75 is going to be 0.8. Okay, so this is going to give us x1 is negative 0.4 plus it's a decimal, 0.8i times x2. So x2 is going to be my free, x2 is x2. So if I look at this in vector form, it's going to look like negative 0.4 plus 0.8i, 1. But if you remember from one of our conversations a while ago, we typically do not leave decimals or fractions in our vector because any multiple will be an acceptable answer, and it's usually just kind of a nicer answer. So if I multiply this by, it looks like I multiplied it by 5 to clear the fraction, I would have negative 2 plus 4i, 5. So it's a little messy with all the decimals, but it's really the same type of problem as all the other ones we've dealt with. So if that follows okay, try lambda 2. It's going to look pretty similar to this one. And if you want to give it a shot on your own first, pause this video, see if you can follow those steps, and try it on your own. Sorry, my dog is in the background. So if we take this second eigenvalue, so the setup is going to look really similar. I'm going to have negative 0.3 this time plus 0.6i, and then negative 0.6, 0.75, and 0.3 plus 0.6i. Don't want to forget my zeros again. Zeros. If I take that second line, 0.75 x1 plus 0.3 plus 0.6i x2 equals 0. 0.75 x1 is negative 0.3 minus 0.6i times x2. Notice that I keep the x2 on the outside. I don't distribute it in, really, because I'm just looking for that coefficient simplified. So we did this algebra before. The 0.3 over 0.75 is going to be 0.4, and then 0.6 over 0.75 is going to be 0.8. So if we look at this in vector form, knowing that x2 is going to be x2, it's going to look really similar to the last one. And again, we can multiply by a scalar to clear the decimal. And we end up with our second eigenvalue. So complex eigenvalues are going to give us complex eigenvectors. And something that's written on the bottom of the last page is something that we've hopefully noticed with these last two problems. So the eigenvalues are going to occur in complex conjugate pairs. You remember that word? So complex conjugate is something that looks like this, is kind of that plus or minus in the middle. So like if 2 plus I is an eigenvalue, we automatically know that 2 minus I is also an eigenvalue. So they occur in complex pairs, complex conjugate pairs, and so do the eigenvectors. If we have, over here, if we have negative 2 plus 4i, we're also going to have negative 2 minus 4i as an eigenvector. So the eigenvalues and the eigenvectors occur in conjugate pairs, which is kind of nice. That means if you find one, you essentially have the other one. So the next problem, problem 10,